welcome. The topic of today's discussion is buffer. In this session, we will discuss about the chemical composition of buffers. The buffering capacity and the buffering range will also be discussed. We will also discuss the mechanism of buffering and the difference between weak and strong acid in terms of their dissociation. The Henderson-Hasselbalch equation, which is important for calculating the pH of a particular buffer system, will also be discussed. Lastly, we will discuss about the important biological buffers that are present in nature and in many systems, and also the buffers that are used in the laboratories all over the world for biological and biomedical research. The word buffer has become very generalized these days and is used in diverse fields of science and literature, but for the same more or less meaning. A buffer state means a country between two potential powers to minimize their conflict. The buffer zone of a reserve forest indicates the region between the core region and the human settlement so as to minimize man-animal conflict. Buffer in railway transportation system means a device to minimize collision between vehicles. Data buffer in computer science denotes temporary storage for input and output data. Finally, in fiber optics, buffer means device for some sort of insulation of one or more optical fiber in a fiber optic cable. Today, we are going to discuss about buffer solutions, which is important in biology and chemistry. Buffer means a solution which has the ability to resist change of pH when acid or alkali is added from outside. Let us use a very simplified example to understand how buffer works. Let us take example of three solutions, 100 ml each at pH 7. One of them is water, the other one is solution A, and the third one, say, is solution B. If 1 ml of 0.01 molar HCl is added to all the three solutions, it is observed that the pH of water drops down from 7 to 4. pH of solution A drops down to, say, 4.5. However, it is observed that in the case of solution B, pH falls from 7 to only to 6.9, which means solution B could resist change of pH when acid is added to it. Solution B is a buffer. This is not only the case for addition of acids, it is equally true if bases are added to these three solutions. For example, if 1 ml of 0.01 molar sodium hydroxide is added to all the three solutions, the pH of water will shoot up to 10, that of solution A to, say, 9.7. However, the pH of solution B or the buffer will go only up to 7.1. Thus, solution B can resist change of pH upon addition of acid or alkali. Thus, solution B qualifies to the definition of a buffer. Before going into the details of how buffer acts, let us consider the dissociation of acids. If HA is a generic acid, then in water it dissociates to form H plus and A minus ions. H plus is the proton which may stay hydrated to form H3O plus, and the A minus is called the conjugate base. The dissociation constant of this reaction Ka is expressed as concentration of A times concentration of H divided by the concentration of HA. Now, some acids are called strong acids. The example is HCl. Strong acids dissociate almost completely in water, as in this case for HCl. HCl dissociates to form H plus and Cl minus, and in the equilibrium mixture, the amount of undissociated HCl is just 0.0004%, while the amount of proton and Cl minus is 99.996%. Or in other words, a strong acid dissociates almost completely in water. In this case of HCl, quantitatively the acid dissociation constant of HCl is expressed as Ka equal to H plus times Cl minus divided by HCl, which at 25 degrees Celsius is 10 to the power of 6, and the pKa, which is the negative log of Ka, is minus 6. Thus, for a strong acid, the Ka is high and the pKa is low. Weak acids dissociate only partly or slightly in aqueous solution, as in the case of acetic acid. Acetic acid is dissolved in water. Almost 98.7% remains as acetic acid. Only 1.3% is dissociated to form H plus and acetate minus ion. In terms of pK and pKa, the Ka of this reaction is 1.8 times 10 to the power of minus 5, which gives a pK value of 4.75. That means weak acids have a low Ka and a high pKa value compared to the strong acids. Now, the chemical composition of a buffer. Chemically, a buffer is a mixture of a weak acid and its conjugate base. In our case of acetate buffer, it is made up of acetic acid and sodium acetate. In a buffer solution, 4 species exist. For example, in the case of acetic acid and sodium acetate buffer system, a small population of proton exists produced from the dissociation of acetic acid along with the bulk amount of undissociated acetic acid. And sodium acetate almost completely dissociates unidirectionally to form Na plus and acetate minus ion. So, in a buffer mixture, the 4 populations are undissociated acetic acid in bulk, small amount of proton, and large amount of Na plus and acetate minus ion. The Henderson-Hasselbalch equation is an important equation to calculate the pH of a particular buffer system. pH equals pKa minus log HA by A minus. Here, A minus is the concentration of the conjugate base, HA is the concentration of the undissociated acid, and pKa is the negative log of Ka, the acid dissociation constant. Now the mechanism of action of the buffer. As is told earlier, in a buffer solution, 4 population exists. The undissociated, in case of acetic acid, it is the undissociated acetic acid, small amount of proton, large amount of acetate ion and sodium ion. Now, when alkali is being added to this solution, the solution becomes OH rich. The small amount of H plus that was there produced from dissociation of acetic acid reacts with OH minus to neutralize it. Consequently, from La Chatelier's principle, the dissociation reaction of acetic acid shifts to the right and more protons are being produced which react with the acetate ion to neutralize it. So, although OH minus ions were added to the solution, they get neutralized and the pH didn't rise because from the undissociated acetic acid, protons are produced to neutralize these OH minus ions. The solution becomes a little bit rich in acetate ion, but the pH does not change significantly. However, when acids are added to a buffer solution, they react to the already present acetate ion and they form back the acetic acid. And since acetic acid is a weak acid, it does not dissociate to form the protons back, so the pH doesn't change. Buffer capacity beta is a quantitative measure of the ability of the buffer to resist change of pH upon addition of hydroxide ions. Buffer capacity beta equals dN by dpH, where dN stands for infinitesimally small increase in hydroxide concentration, which results in dpH, an infinitesimally small increase in pH. The extended mathematical expression of beta shows that there are three regions where the buffer can show its buffering capacity. One at a low pH, the other at a high pH. However, the one that lies at the middle is important to us, and this buffer capacity region is close to the pK value of the constituent acid. This is important because this buffering capacity is proportional to the concentration of the constituents of the buffer. Buffer range denotes the pH over which the buffering capacity of a buffer is optimum. It has been observed that at pH close to or equal to the pK of the acid, the buffering capacity of a buffer is optimum. However, buffer range is somewhat arbitrarily defined as the pH range over which the optimum buffering capacity of the buffer does not decrease by more than 30%. For our acetic acid sodium acetate buffer system, the pKa of acetic acid is 4.8, and it has been observed that the optimum buffer range of sodium acetate acetic acid buffer is pKa plus minus 1 pH unit, that is from 3.8 to 5.8 pH. This table shows some of the buffers that are widely used in chemistry and biology. Their buffering range spans from pH 1 to pH 12 or even more. However, for biologists like us, we are interested in a region of pH 5 to pH 9. So, potassium phosphate buffer and sodium phosphate buffer are of importance to us. Now, here are some important buffers that are widely present in biological system. One such example is the H2PO4 minus and HPO4 2 minus buffer system, where H2PO4 acts as the proton donor and HPO4 2 minus acts as the proton acceptor. The Ka, or the equilibrium constant of the reaction at 25 degrees Celsius is 6.23 times 10 to the power of minus 8, and the corresponding pKa is 7.21. Another important buffer which is widely found in nature is the bicarbonate buffer system H2CO3 and HCO3 minus, where H2CO3 acts as the proton donor and HCO3 minus acts as the proton acceptor. The Ka of this buffer system at 25 degrees Celsius is 7.9 times 10 to the power of minus 7 with a pKa value of 6.1. We know that buffer maintain the pH. In absence of buffer, the pH will get drastically changed. What can happen to biological system if pH could not be controlled? The ionization property of macromolecules are of extreme importance in biological system. If the pH changes drastically, the ionization property of many important biological macromolecules may change. This may lead to a serious disruption in the enzyme-substrate reaction. The properties of the enzyme and substrate may get altered such that enzyme reaction may become slow or even stop. The structural macromolecules, whose 3D conformation is important for the biological structure and function, may get altered, and hence the entire system may collapse. Blood is an important buffer. Since blood percolates all over the body, it is important to maintain the pH of blood. Yes, the pH of human blood is maintained very precisely at pH 7.35 to pH 7.4. Blood contains at least 3 buffer systems. The phosphate buffer and the bicarbonate buffer present in the blood plasma, and the plasma proteins present in blood can also act as a buffer because of the presence of side chain carboxylic acid groups and side chain amino groups. Both of these groups have the ability to donate and accept protons and act as a buffer. This table shows list of buffers that are widely used in laboratories all over the world for biological and biomedical research. It is important to see that their buffer range lies between pH 5 to pH 9, well covering the biological pH which is close to 7. A researcher needs to know which buffer to be used. He has to choose from this list such that his compound of interest doesn't react with any compound of these buffer systems. He will also need to know that the buffer should cover the pH range which he is interested in. Finally, we come to the concluding part of our discussion, and these are the key take-home points. Buffers are solutions which have the ability to resist pH change upon addition of acid or alkali from outside. Most of the biological reactions in nature occur at a very narrow pH range, so it is very important to control the pH. And biological systems use buffers to control the pH at such a precise range. Chemically, a buffer is a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. Strong acid dissociates completely in water, whereas weak acid dissociates only slightly. Bulk of it remains as undissociated. Phosphate and bicarbonate are the most abundant buffers found in nature. All buffers have a buffer capacity and a buffer range. Buffer range is the pH range over which the buffering capacity of a particular buffer is optimum. Buffer capacity denotes the quantitative strength of a buffer. At least 3 buffer systems exist in blood to maintain the pH of blood at a very narrow range. These are the phosphate and the bicarbonate buffer system present in the plasma, and the third one is the plasma protein through the free carboxyl group and the amino group present on the side chains of the constituent amino acids.